What is up, everybody? Here we go. Another day, another dynamics problem. All right. It says gear A is in mesh with gear B as shown. If A starts from rest and has a constant angular acceleration of 2 radians per second squared, determine the time needed for B to attain an angular velocity of 50 radians per second. Okay. So the whole idea is we have this guy, and it's rotating, right? So it's rotating at whatever the angular acceleration was. We want to translate this rotation into this rotation. And not only are we going to translate from one object to another, we're going to do we're going to do some sort of kinematics, right? Because they want us to go from acceleration to velocity. So it's not like we're going from acceleration to acceleration. Okay. So let's see. They give us some information. Starts from rest is important. All right. That means I know that if we're doing like a I guess state 1, state 2, we know state 1 has a velocity of 0. We know that the acceleration is constant, and they give us the value of it. So if the angular acceleration is constant, that means the linear acceleration is constant, all right? And then they want to find the time, right? Determine the time needed. But they tell us that the new velocity is going to be 50. All right, so that's not a big deal. We just have to figure out what's going on when it comes down to the point of contact, right? So as you look at point A and point B, or rather wheel A and wheel B, let's just look at this point of contact right here. So that's gonna be our focus. You've got to know that first off, we're doing pure kinematics, right? It's pure kinematics. How do we know that? Kinematics is the study of motion. How do we know it's pure kinematics? They don't say anything about mass, right? They say nothing about mass, kinematics. That's position, velocity, acceleration, and time, or angular position, angular velocity, angular acceleration, and time. Time is constant, obviously. So you've got to know how to relate those two things. So we got positions, velocities, blah, 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 blah. You've got to know the fundamental definitions, right? And you got to know how to relate them. So let's see. What you also have to know is when it comes down to the point of contact, a lot of students are going to say this. They're going to say that this alpha for block A, or wheel A, excuse me, is the same as alpha for wheel B. The alpha for A and the alpha for B are not the same. When two objects are in contact and they're rotating, it's not their angular values that stay the same. Angular value stays the same for a specific body. What do I mean by that? If I were to look at the outer edge versus the center, versus like somewhere towards the middle versus the center, all of these guys are going to rotate with the same speeds and the same angulars, right? On the same body, the angular value is the same. We call it a global term. However, when two objects are touching the point of contact, the same linear variable is going to exist. So what I'm trying to say by that is it's not the angular acceleration of A equals the angular acceleration of B. It's the tangential acceleration of A equals the tangential acceleration of B at the point of contact. So this whole idea exists for that little green dot, all right? So what I'm going to do is I'm just going to, I guess I'll put it in purple. No, I'll leave it in red. And I'll just say a T for the little red, okay? So we know that. The thing is, though, we don't know the tangential acceleration of A or B. But it's okay, because we know the angular acceleration of A, which means we know the tangential acceleration of A. Okay, so all I have to do is give the definition of the tangential. So we know that A equals alpha cross R. Okay, so I'll know that. And then you do have to know that by heart. Unfortunately, it's just one of those things. And so all I have to do is plug and chug this guy into both renditions of the alpha. Okay. And what it's going to do is it's going to give me a way to rewrite this equation in an angular format. So I got alpha of A, R, A. And then I got alpha of B, R, B. Okay. So that's not that big a deal. With that being said, I'm going to rearrange it for alpha of B. Why am I going to rearrange it for alpha of B? Because alpha of B relates to WB, all right? But I can't find alpha of A relates to WB. It's not going to work. So if I can find the information about B, then I'll be able to kind of do the more kinematics to get to my answer, okay? So keep it moving. We're just going to say alpha of B equals, I got alpha of A RA over RB. I know those values. Alpha A was 2, RA is 0.025, and then RB is 0.1. All right, so that being said, alpha of B is going to be 0.5, and that'll be radians per second squared. Okay. Now, that's not the answer, actually. I don't know why I just set it up like it was the answer. That's not the answer, but that's a very important piece of information. Why is that an important piece? Why is that an important piece of information? Let's think about it. So they said in the problem that the wheel A has a constant angular acceleration. So we know if the wheel A has a constant angular acceleration, so A constant, we know it's going to be A and alpha because they're related, right? Well, think about it. We know that the tangential acceleration for the point of contact between A and B is going to be the same. And if the acceleration for A is constant, that means that the acceleration of B is constant. So for B, we also have a constant A and alpha. Okay. So B having a constant A and alpha is very important. So I'm going to just kind of underline that. Why? That's because I cannot use the constant acceleration equations. I'll put it in green or whatever. I don't want to keep using red. So I'll say for B, use the constant acceleration equations, okay, to find W. I could try to use W equals, or A equals W over T. Like I could try to use this, alpha equals dW dt, and then do like the integral and all of that jazz. So you could just say W equals the integral of alpha dt. But the thing is, it's going to go from 0 to t, and then you're going to end up with a function. And then you have to solve that function for time. Well, for those of you who like calculus, you can do that. That's great. Or you could just realize that somebody did that a long time ago and came up with the constant acceleration equations. And so alpha equals delta W over delta T. Let's see, delta theta equals W naught times time plus 1/2 alpha T squared. And all I've done is turn position into angular position, velocity into angular velocity, and acceleration into angular acceleration. W final squared equals W initial squared plus 2 alpha delta S, right? So let's see. I think I'm going to use this one since it has time. It has W, but it doesn't have a position. They never gave me position, so that's going to be an easier one to use. So all I have to do is set up for time. Time equals, it's going to be 1 over alpha, and then I'm going to multiply by W. Yeah, 1 over alpha times delta W. Delta W is going to be W2 minus W1. So I got W final minus W initial over alpha. Cool. I know W final is going to be 50. They told us that in this part right here. So I know this is going to be 50. They said the problem starts from rest. So W is 0. And then the alpha I found out was 0.5. That's where this guy comes in. And that's why that was so important. All right, cool. So that being said, 50 over 0.5 is what, 100? So my answer is 100, and that will be seconds, and that is the answer. So, not a bad problem at all. Pretty straightforward. You just have to kind of realize what's happening at the point of contact. Realizing the fringe or the connective physics and the rules and the equations and like what goes, like knowing that it's not the alphas that are connected, but the tangentials that are connected, and the fundamental definition of some of these things. In addition to that, knowing that it's constant acceleration, which makes it easier to use algebra versus calculus. That's basically the heart and soul to all of this. Okay, so a lot of people like to focus on just knowing equations, but it's all about knowing how the equations work, like why, what's the theory behind it, what's the concepts. Okay, so that's that. If you like these videos, please don't forget to go and actually click the like button, go subscribe to the channel, make sure you hit the little bell. Got a goal, trying to put up as many mechanical and electrical engineering videos as I can, just because these classes just shouldn't be that hard, right? So with all that being said, thanks so much for your time, and I hope this helped.